Alright, in this video we're going to be talking about a very famous problem from the 5th century BC. This is the time period before Socrates, Plato, and Aristotle, and it's called Zeno's paradox. Zeno's paradox. And this paradox was invented in order to challenge our common sense notions of time, space, motion, and even mathematics and geometry. So we've drawn a little diagram, a little model of what this paradox involves. So up here on top we have our brave Greek warrior Achilles, and on the bottom we have our trusty turtle Benny. This is Benny. So these two are involved in a foot race, as you can probably tell by the little flag over here. So Benny is starting ahead of Achilles at this position that we've called x1, and then Achilles is behind Benny at the position that we call x0. So let's see what happens, at least in Zeno's head, when the firing gun goes off and these two begin racing. So the first thing Achilles needs to do in order to win the race against Benny is he needs to catch up with him. He needs to catch up with him, he needs to pass him, and then he needs to go on to win the race. Now, for us, we're going to say that Achilles is running twice as fast as Benny. So yeah, he's running twice as fast. So we're going to start out, and Achilles is going to run from x0 all the way to x1. No problem. So now he's arrived at x1. Now, during this time period that we're going to call T1, Benny has also moved. Benny has only moved half as far, because Benny is, twice as slow, but Benny's at a new position, and this new position we are going to call x2. We'll say this is x2. So Achilles has the same problem right now that he had before the race even started. He's behind Benny, and he needs to catch up with him. So he's in x1, he needs to get to x2, and he says, alright, I'll just do it again. So Achilles is now going to run from x1 to x2. And now that he's safely arrived, Benny is still ahead of him, because Benny is right here at x3. So I think that you can sense a pattern emerging. We can keep doing this with our x's, forever. Benny can keep inching forward as Achilles tries to catch up to him. We can divide space into these infinitely small subdivisions, as they get smaller and smaller. So let's not forget that for each of these divisions of space is a division of time. So we'll call this one T2 after T1, and then up here we have T3, and again that just goes to infinity. So in keeping sense of what all of these T1s and T2s and T3s mean, let's just say that the amount of time required for Achilles to catch Benny is equal to the sum of T1 plus T2 plus T3 plus ... all the way up to t to the n. So I'll just write t to the n here. And this notation is common in mathematics, but for those of you who don't know, t to the n just means t to the highest order integer. Essentially, t going on forever and ever. Because, like I said, there's an infinite number of these time periods, getting smaller as they go, to correspond with these infinite divisions of space, these x's. So this is where Zeno makes the big point in his argument. Zeno says, in order for Achilles to catch up with Benny, Achilles has to run an infinite number of spaces. In order just to get to where the turtle is, he has to complete literally an infinite number of tasks. He has to go from x0 to x1, and then so on, all the way up to x to the infinity. And if that wasn't bad enough, not only does he have to complete an infinite number of tasks, he has to do that with each task taking up some amount of time. All of these t's over here are a positive, finite, real amount of time. They're getting smaller, but there's actually an infinite amount of them. And it's here that Zeno makes the argument that if you take an infinite sum of anything, it's going to equal an infinite number. So he says, if you keep adding these t's together, no matter how small they are, because there's an infinite number of them, the total must either be infinite or arbitrarily large. And if that's the case, Achilles can never catch up to Benny because the amount of time required to catch him is infinite. I encourage you to pause the video, take a minute to sort of reflect on that for a minute. What has Zeno just said? He's just said that motion is impossible because in order to move anything from point A to point B, you have to move it first to the infinite points between A and B. So, you know, if A's here and B's here, you can literally divide this into ever smaller amounts of space, and you have to get through all of them. You have to complete an infinite number of tasks just to complete one task. I mean, that's mind-boggling. How do we deal with that idea? So pause the video and think about why Achilles can pass Benny in real life, but he can't pass Benny in the model. That is our example of philosophical reasoning that Zeno is pushing us towards. Again, challenging those common sense notions. So now that you've probably had a minute to think about it, let's go into why this isn't necessarily the case. So those of you who are students of calculus know that just because you're adding an infinite amount of different items, if those items become small enough fast enough, they will actually converge to a finite sum. In English, what that means is just because you're adding an infinite number of things doesn't mean the total of those things is going to be infinite. If that seems like a strange idea, and it might, let me just illustrate it with an example from geometry that ties back to our little foot race. So I'm going to draw a square really slowly because I'm bad at drawing. Draw a square. And we're going to imagine that this square is the total amount of time that it takes Achilles to catch up to Benny. Now we said that Achilles is running twice as fast. Achilles is running twice as fast as Benny, which means that T2 is half of T1, T3 is half of T2. You know, as these distances become smaller and smaller, the times required to traverse them become smaller too, and we're adding them all together. So let's just say that T1 is going to be half of the total amount of time required to catch up to Benny. Now, T2 is half of T1, so half of 1/2 is a quarter. So here's a quarter. And then T3 is an eighth, and we can do this. So we'll say that's an eighth. And then I'll go to a little bit of a finer brush here. And then we say, okay, there's our 1/16th, our 1/32nd, 1/64th, and you can see the pattern. As we're adding an infinite number of these things, we're never going to get outside of this box. So in fact, we've managed to add these infinite number of divisions without getting infinity. In fact, it's not even close to infinity because it's 1. It's 1. All of these infinite divisions add up to 1. And this simple example from geometry is actually a very elegant explanation of some of the underlying ideas in calculus. And this is old. This is a very old idea. This comes from a guy named Archimedes. And what he did, in addition to discovering this concept, is he used this diagram to draw a very cool little spiral. And this spiral continues on forever and ever. And what this spiral shows us is that we can put infinity into a container. We can take an infinite number of items and put them together and get something that we can actually hold in our hand, or something that we can see in the form of this foot race. That's a very exciting idea. That's very interesting to think about, and that's the point of philosophy. You know, all this argument over x0s and x1s and time and infinite sums, the point of it is not to disprove necessarily that Achilles is going to never catch up to Benny. He is. You watch a race, the faster runner wins. That's common sense. But because we've used Zeno's ideas and because we've done the reasoning, we've came into insight. And this insight in mathematics, or this insight in ethics or aesthetics or metaphysics, is what philosophy is after. It's why it asks the big questions. Because the process of asking big questions sometimes leads you to beautiful answers, such as this spiral.